All right, good morning. Well, or afternoon or evening, I guess, depending on when you're watching this. But here are the notes for Rolle's theorem. This is just a brief addition to section 3.2. And it should be pretty obvious, but it's worth writing it down so that you understand what the theorem is and what the conditions are. So the theorem itself states that first we're going to have f, and if f is continuous, so let f be continuous on a closed interval from a to b, and differentiable on an open interval that corresponds to a and b. Okay, so it's the same setup as the mean value theorem. So assuming we have those conditions met, if f of a equals f of b, then there is at least one c value in the open interval from a to b such that f prime of c equals 0. Okay, so this is Rolle's theorem. Okay, so let's look at a picture to kind of get some intuition as to what's going on and why this has to be the case. And so let's say we have some, smooth continuous function, and let's say this point corresponds to A, and now we want another point B that has the same coordinates, right? That's what this part means here, that if you plug A in and you plug B in into the function, doesn't matter, you're going to get the same exact y value, okay? So obviously, this is a continuous function. It's differentiable, right? There's no like discontinuities or any cusps or corners, anything like that. So this is continuous, this is differentiable. And so now what does this part mean? This means that the slope of the function, the instantaneous rate of change, has to be 0 at least once, somewhere in between these 2 points. In other words, the tangent line of the graph has to be 0. The slope has to be 0, has to be flat. So if you look at the picture here, that seems pretty obvious that right at this point, we have a tangent line with a slope equal to 0. And that's what this means. So this would be the c value here. So f of c would have to be equal to, f prime of c would have to be equal to 0 in this picture right here at this point. Okay? So intuitively, hopefully it makes some sense. If you start at a point and end at the same point, okay, you're either going to be flat the whole way through, in which case the slope or the derivative is always going to be 0, okay? Or if you go up, well, at some point you got to come back down, right? And so that means the slope will be 0 at that turning point. Or if you go down, like we did in this case, then we will have a 0 slope down here. Okay, just to illustrate again, let's do a slightly different picture. So let's say this is our A and B values. And let's say here is our start and end. So there's our closed interval. And let's say we do something like this. Okay? Rolle's theorem says that if this is continuous, which it is, and the derivatives exist, which they do, at some point between A and B, there's got to be at least one time where the slope is 0. In other words, the tangent line is flat, right? So that's going to happen here. That's going to happen here, here, and here. Okay, so in this case, we actually have, looks like 4 C values. Okay, so I'm just going to call them C1, C2, C3, and then this one would be C4. Okay, but that's essentially what Rolle's theorem guarantees. If we start and end at the same spot, at some point, we're going to have a slope of 0. In other words, the derivative of the function has to equal 0 at least one time. Here's where it was once, here's where we have several. So now hopefully that kind of makes sense. Now let's look at an example. First question, let's say we want to determine if Rolle's theorem applies to f of x equal to sine of x on the interval from pi over 2 to 3 pi over 2. Justify. So why or why not? All right, so first we got to check the conditions. The conditions are, first, is this a continuous function? Sine of x, we know what sine of x looks like. Let's draw a little picture. Here's one period of sine of x, right? Here's one period of sine of x. Obviously it continues, and so from pi over 2 to 3 pi over 2, that would be from here to here. So from this point to this point, okay? Yes, we're continuous. There's no issues with taking slopes or derivatives here, so it is differentiable. And now, so the two conditions are met. Now the last piece is, does f of pi over 2 equal f of 3 pi over 2? So that's the question. And so you can either look at the picture or just plug these in, right? The sine of pi over 2 is 1. So that's right up here, right? And the sine of 3 pi over 2 on the unit circle is negative 1. So that's this point down here. Okay? And so the answer here is no. These two are not equal to each other. Therefore, this is the symbol for therefore. Rolle's theorem does not apply. Okay? One more problem. So this one, find the value or values of C guaranteed by Rolle's theorem for the function f of x equal to sine squared x plus cosine x over the interval, let's go 0 to 2 pi. All right, so first, okay, this is a continuous function. This is differentiable. Okay, and if you're wondering how I'm doing that without looking at the graph, I know that sine of x is continuous. Squaring it isn't going to do anything. Cosine of x is continuous. Adding those two together is still going to keep it continuous. You can take derivatives all day for sine and cosine, right? So that's not an issue. Now let's check what is f of 0. F of 0, if I plug 0 in, will be the sine of 0 squared plus the cosine of 0. The sine of 0 is 0. The cosine of 0 is 1. And now if I plug in 2 pi, and hopefully you already know the answer to this, these are in the same position on the unit circle, right? So that's not going to change anything. But this is what it would look like algebraically, right? The sine of 2 pi is still going to be 0. The cosine of 2 pi is still going to be 1. So yes, f of 0 and f of 2 pi are equal to each other. Okay, so now we know that Rolle's theorem can be used here, and we can definitely figure out what c values are going to have a 0 derivative. So that's the next step. Once we verify that we can use Rolle's theorem, now we take the derivative of the function. So use the power rule. We got 2 sine x. And now don't forget we have to do the chain rule, right? So the 2 comes out. So you have 2 sine x, and then take the derivative of the inside. Gives you cosine x. Cosine x derivative, let me change that. That's going to be minus sine x. And now we want to set that equal to 0 because Rolle's theorem says that we can do that. Okay? And so now if I take those values, or actually let's factor first. So let's factor out a sine x, since that's common to both, right? You're going to be left with 2 cosine x minus 1. And now to find the values that we're looking for, zero product property tells us that sine of x equals 0 and 2 cosine of x minus 1 equals 0. In other words, cosine of x equals 1/2. And so we're going from 0 to 2 pi. However, let's go back to the theorem real quick. The theorem guarantees on the open interval there's going to be values, right? And so for this, when we are actually looking for our c values, c must be, so c lives in the interval from 0 to 2 pi, open. Okay? So keep that in mind. So now as I start solving, x, this is pretty easy, right? The sine of x will be 0 on the x-axis. So at 0, and at pi, and at 2 pi, and that's good enough. So the only thing I can list from there is pi, right? Because I cannot include 0 and 2 pi. We never include endpoints when we're doing these problems here. Just everything in between, okay? Now over here, cosine of x equals 1/2. So we could have, what is that, pi over 3, right? Pi over 3 in the first quadrant, and then we also want the fourth quadrant partner. That'll be 5 pi over 3. Okay, and so those would be the values guaranteed by Rolle's theorem where the derivative is 0. Okay, now, are there more? Yeah, but just in the open interval from 0 to 2 pi, this is it. Okay, so these are the only ones that we can report by Rolle's theorem. All right, so hopefully that helps a little bit. We'll see you guys next time.